Hello students, welcome to Educate. In this class, we will discuss firstly about Bohr's model for hydrogen atom, and based on that, we will solve some numerical questions. Okay, so firstly let's see Bohr's model for hydrogen atom. About that, in rough I have given you the idea. Now let's see about this one here, Bohr's model of hydrogen. About this one is that Bohr's atomic model states that the electron in the hydrogen atom, the electron revolves in a fixed circular path that is called orbit. Electron revolves in hydrogen atom. The electrons revolves around the nucleus in a fixed circular path that is called orbit, and there will be a number of stationary states or allowed energy states. That will have the electron revolves in a fixed circular path that will be called orbit, and that will have fixed energy and that will have certain radius also. Okay, so for first state it will be called ground state, or that is called Bohr's orbit. This one is also called first energy state. The first orbit of the electron, that will be called Bohr's orbit. So this is also called Bohr's orbit, that will have fixed energy. That is, energy is, you will study there, minus 2.18 into 10 to the power minus 18. In case of electron, first electron, that will be second electron here, second energy state. That will be second stationary state. In that case, energy will be minus 2.18 into 10 to the power minus 18, that upon 2 square. Same in third state, energy will be minus 2.18 into 10 to the power minus 18, that upon 3 square. So electron revolving around the nucleus in a fixed circular orbit, in a fixed circular path, that will be called orbit, and that will have a definite energy whose value will be minus 2.18 into 10 to the power minus 18 upon n square, where n will be here 1 for the first orbit, 2 for second orbit, 3 for third orbit, like that. Second one is the energy of electron will not change with time if the difference of energy between second and first, that will get absorbed by the electron. Then the electron can jump into the next energy level, and there is no stationary state between the first and the second orbit. That is this one. The frequency of radiation absorbed or emitted when transition occurs between two stationary states. So that is same here. The difference of energy will be that one. So difference of energy, like if electron will fall from second cell to first cell, then this energy, that is this difference of energy, this energy minus this energy, that will, if this electron will emit that amount of energy which will be equal to the difference of the second energy level minus first energy level, then electron will fall from higher energy level to lower energy level. The maximum energy of electron will be 0 when it will be not influence of the nucleus. When the electron will come closer to the nucleus, then energy of electron will decrease. Okay, so that is here. Angular momentum, that's value is given mvr, angular momentum, and that is equal to nh upon 2 pi. About that we have also discussed in short in the previous class. Radius of that orbit, radius of any orbit, that will be according to n square a naught. A naught if value is 52.9 picometer. Energy RH minus RH upon 1 upon n square, that is minus 2.18 into 10 to the minus 18. About that we have already discussed. About already we have given the explanation about this one, but we have not solved the numerical questions related to this one, Bohr's orbit. Explanation of line spectrum of hydrogen, about that we have already discussed. Okay, now let's see. Watch out this question. Question is, you have to find out frequency and wavelength of photon emitted when electron will fall from n equal to 5 to n equal to 2. You have to find out the frequency and wavelength of photon when electron will fall from n equal to 5 to n equal to 2. So first of all, we will find out the energy of electron, in fifth cell. That will be equal to minus 2.18 into 10 minus 18 upon 5 square. That will be and electron jumps into second energy level. So that will be here. Electron comes into second energy level from the first energy level. So difference of energy that will be emitted by in the form of radiation. Difference of energy of the electron that will radiate in the form of radiation. So E2 minus E1, E2 minus E5, that will be the energy of radiation. So it is the energy decrease in the energy of electron. So this is the decrease in energy of electron. So how much energy will emitted? So that will be the positive value. So that will be here. How much? That will be multiply this one, and you will get the energy emitted by the photon. So because the decrease in the energy of electron, decrease in energy of electron, that will be equal to the energy emitted, that will be equal to the energy of photon emitted. Okay. This one is the energy, decrement in the energy of electron, minus negative sign, that means decrease in the energy of electron. Now, so this is the value of decrease in, so energy of photon emitted when this one state will be positive sign here, will be here, so that will be positive. So that will be here, this much. So energy of photon emitted here, that will be 4.5 into 10 power minus 19. That much joule. Okay, this is the decrease negative sign, that means decrease the energy of electron. So energy of photon will be this much, energy of photon that much, and not this one. So now you know energy of photon E equal to h nu, frequency we will have to find out. So energy that much, so frequency of photon will be, energy is 4.5 into 10 minus 19 joule, that upon here Planck's value 6.6 into 10 power minus 34 joule into second. So joule cancel out, that will remain second here. So 4.5 divided by 6.6, that you will have to do. That will be 6.91 into 10 minus 34 will go above, so that will remain 10 power 14. So that will be 6.91 into 10 power 14 second inverse, or 6.91 into 10 power 14 hertz. That will be the frequency of photon. Now you know C equal to nu lambda. Nu you have calculated, so lambda will be 3 into 10 power 8 meter per second, that upon 6.91 into 10 power 14, that will be second inverse. So that will cancel out, so meter will left. 3 divided by 6.91, 10 power 14 will go, so that will come here. So 14 minus 8, how much? So firstly 3 divided by 6.91, that do firstly 3 divided by 6.91, that comes 434, 0.434 into 10 power here 14 minus 8, 6, so 10 power minus 6, so that will be, can be written as 434 into 10 power that much micrometer, or 10 you may convert into 10 power minus 9, so that much nanometer, so that much nanometer. Answer is that. Okay, so that is the procedure to solve the question. Question is, calculate the energy associated with the first orbit of He plus. What is the radius of this orbit? What happened? He plus is a hydrogen-like species. He plus is a hydrogen-like species. Since He plus contain only one electron and it contains 2 protons in the nucleus. So energy of hydrogen-like species, that will be more than that of, that means energy of the electron of He plus will be greater than that of hydrogen, because in the He plus there is 2 protons, so centripetal force will be more. That is the force of attraction operating between the nucleus and the valence electron. That means force of attraction operating between the nucleus and the electron, that will be greater. That will be greater, so energy will be also greater. So through how much value the energy will be? So for hydrogen-like species, the energy will be multiple of Z square. So here hydrogen, helium, He plus, atomic number is 2. So that's why what's the energy of that hydrogen, electron of hydrogen? That when multiplied by 4, that will be the energy of He plus. So energy of He plus, energy of the electron of He plus, that will be equal to your energy of hydrogen is minus 2.18 into 10 minus 18 upon n square. N is here what? First orbit. So 1 square, that into Z square. So Z square, Z here is 2. So that will be equal to minus 2.18 into 10 minus 18 into Z here is 2. So that is 4. So multiply here 2.18 into 4. How much it will be? So 8 4 ja 8.72 into 10 power minus 18. That much joule energy of this one. Now what's its radius? What happened in case of radius? In case of radius, since there is 2 proton in the nucleus, in case of He plus, there is 2 proton in the nucleus, so it will attract the valence electron very more extensively than the nucleus of hydrogen attract the valence electron. So hydrogen energy radius of He plus, that will be here, that divided by Z. So you know radius of hydrogen as R naught n square. So for hydrogen like species, for hydrogen, that means, so for hydrogen like species, that is suppose He plus, so that will be R naught n square, that upon 2. Z here is 2. So hydrogen for this one is R naught n square. For hydrogen like species, the radius will be R naught n square upon Z. So R naught is how much? 0.0529 nanometer. So R naught is 0.0529, that much nanometer. That one into, it is in first orbit, so 1 square, that upon Z is 2. So that divide them, you will get 0.0529 divided by 2, that will be 0.026, 0.026, that much nanometer. That is here, okay, 0.02645 nanometer, that is here. Now then after here we will discuss about this topic towards quantum mechanical model of the atom, about that. Then after quantum mechanical model of the atom, there was various theories which forced to consider about the dual behavior of atom. And first one is, that is dual behavior of atom, matter. So dual behavior of matter, that is de Broglie's wave equation. Dual behavior of matter, that has been associated, that has been proposed by de Broglie's. The de Broglie stated that whenever any object will be in motion, then that object will possess the particle characteristic as well as the wave characteristic. Whenever any object will be in motion, then that object will possess the particle characteristic as well as the wave characteristic. So when there will be particle, so that will have momentum, and when it will act as a wave, so that will have wavelength. So relationship between the wavelength and the momentum has been provided by the de Broglie's, and he stated that the relationship between, he gives the relationship between the wavelength and the momentum as lambda equal to h upon mv, or lambda equal to h upon p. So it is p, that is momentum. That is not only valid for the electron, but that is valid for all the objects. And the macroscopic object, that means object to which we observe in our day-to-day life, and their masses is large. So in case of macroscopic object, the value of wavelength is too much less, that it is difficult to observe that wavelength. Okay, so that will be discussed by the numericals, and then after you will realize that whenever any object be in the motion, that also possesses the wave characteristic. So let's see about this question. It is asking that you will have to find out the wavelength of a ball. The mass of the ball is 0.1 kg, that means 100 gram. The mass of the ball usually 100 gram, and that is moving with a velocity of 10 meter per second. How to calculate? So by de Broglie's equation, you already know lambda equal to h upon mv, and wavelength you have to find out. So very simple here, h equal to 6.6 into 10 to the power minus 34 joule into second. That means upon mass of the ball is 0.1 kg and velocity is 10 meter per second. So that is here. That will get cancelled out. So that will be equal to 6.6 into 10 to the power minus 34. Okay, it is here velocity in meter per second. Second, cancel out. Okay. And mass is here 0%, and here kg it is. So joule by kg. So that will be what? Wavelength. That will come in. Let's see once again. Lambda equal to h upon mv. So lambda equal to 6 here, 6.6 into 10 to the power minus 34 joule into second. That upon mass of the object is here 0.1 kg. Into velocity of that object is 10 meter per second. So what will happen? That will be equal to this one cancel out. So 6.6 into 10 minus 34. That much meter. That much. Now watch out, when a cricket ball is there by which you play, their mass is not too much greater. That mass is less, that is 100 gram. 100 gram is not too much. So their wavelength is 6.6 into 10 to the minus 34 meter. So you watch out how much value, less value is of the wavelength associated with that cricket ball. Okay. About the joule you know already. Joule, so energy you can find out here. Now let's see about this question, 2.13, question number. Let's see about mass of electron has been provided. This much. Kinetic energy has been also provided, and it's asking the wavelength. So kinetic energy you know already. So what's the relationship between kinetic energy and momentum here? Because you know lambda equal to h upon mv. So here kinetic energy is given. So what's its momentum? Firstly, you will have to find out that mass is given. And kinetic energy that is given. Kinetic energy you know here, kinetic energy that is equal to half mv square, and momentum is mv. So what to do here? How to convert? So to calculate in this one, if you divide by p here, v here, m, if you multiply this equation by m, so kinetic energy here that is equal to half into m v square into m above and m below also. So that will be equal to m square v square 2m square v square upon m. This is momentum square. So kinetic energy will be equal to 2 into momentum square upon m. Okay. So momentum you can find out. Momentum will be here. Momentum will be kinetic energy m into kinetic energy So momentum will be equal to m into kinetic energy, that upon 2, and that whole under root. Okay, momentum you've calculated, mass you know, so lambda equal to h upon p, lambda equal to h upon p you know already, so that will be equal to 6.6 into 10 minus, okay, p you can calculate here directly, so p will be how much, here calculate, so that there will be simplification. So p will be equal to, mass is given here 9.1 into 10 minus 31 kg, that into kinetic energy, directly I shall write here about that unit, because unit here not so much space, so that much into kinetic energy is given, that becomes 13.65, and their under root you will have to find out. .69, 10 is power 31 minus 25, 6, 10 is power, oh no, both will get added, that much. So momentum h upon p, that will be 6.6 into 10 minus 34 joule second upon 3.69 10 power minus 28, that kg meter per second. So now 6.6 divided by 3.69, so in this way you can calculate what's there, what this was the method, by that you can calculate that here, that is there is relationship between kinetic energy and momentum, that is, and by that you can find out the wavelength associated with the electron. Question this one here, calculate the mass of photon with wavelength this much. So wavelength is given, energy of that photon you can find out, energy of that photon you can find out, and when energy you will find out, that is kinetic energy of the photon, that when you will find out, then you can find out the momentum also. Okay, so here photon velocity is that much, mass you will have to find out. Okay, so in this way you can find out the wavelength. Okay, mass of photon with wavelength this much, so velocity is given here, so in the book here that's already very easily solved. Lambda is this much, velocity of photon, that is velocity of light, so mass will be h upon lambda v, because lambda equal to h upon mv, So m will be equal to h upon lambda v. That is here. M equal to h upon lambda v. Data has been put and answer completed. Okay. Next one is about next step about the Heisenberg's uncertainty principle. That is next concepts which led to the proposal of quantum mechanical model of atom was Heisenberg's uncertainty principle. Heisenberg's uncertainty principle states that we cannot calculate both position and momentum of electron. We cannot calculate the both position and momentum of electron simultaneously after a certain accuracy. So when we will multiply the inaccuracy in the position and momentum, that is here given delta x delta p, that will be inaccuracy in position into inaccuracy in momentum, that will be always greater than or equal to h upon 4 pi. So at most the both position and momentum of electron we can calculate simultaneously till the limit of h upon 4 pi. So inaccuracy in the position and that of the momentum of the electron will be always greater than or equal to h upon 4 pi. What's the reason here? Firstly, watch out here. If the standard selected will be large, then there will be inaccuracy. Then accuracy more be the value of the unit, more be the inaccuracy. So to calculate any quantity accurately, we will have to take the unit smaller. Like that, if 1 kg 1 kg potato you will purchase, maybe you will get 50 gram extra. But if you will take the unit as 50 gram, then inaccuracy will be less than 50 gram. So that is here, that is more be the value of unit taken to measure, more be the inaccuracy. So to calculate the position of electron, the photons used to calculate the position of electron, the photons used will be of a smaller wavelength. But when wavelength will be smaller, then energy of photon will be large. When energy of photon will large, so when here the striking photon will fall to the electron, then the kinetic energy of, that means the photon will impart the kinetic energy in the electron. So kinetic energy of electron will increase. So what's the velocity of electron? Their velocity will increase. So when you have calculated the position of electron accurately, then you have calculated the momentum or the velocity of electron inaccurately. And when you will take the photon of larger wavelength, then there will be inaccuracy in the position of the electron. So that's the reason Heisenberg's uncertainty principle states that we cannot calculate both position and momentum of electron accurately after a certain limit. That is, delta x delta p will be always greater than or equal to h upon 4 pi. That is inaccuracy in the position. When we multiply inaccuracy in the position and the inaccuracy in momentum, then that value will be always greater than or equal to h upon 4 pi. Okay, so that is here. So about the significance we will go there, but before that let's see how to solve the numericals based on Heisenberg's uncertainty principle. So let's see here. Here, a microscope using suitable photon is employed to locate an electron in an atom within a distance of 0.1 angstrom. What is the uncertainty involved in the momentum of its velocity? So you already know what is the uncertainty involved. So uncertainty here, delta x delta p, that is here. So delta, you already know delta x delta p is greater than or equal to h upon 4 pi. So that will be equal to, and here delta momentum, you know, velocity is given. Okay, uncertainty the velocity you have to find out. So this one given here. So momentum, this momentum has been expressed as m delta v here. So that's why here delta x delta p equal to h upon 4 pi. That's why h delta x into m into delta v, that will be equal to h upon 4 pi. That is mistake. Here is printing mistake. That is delta x delta p, inaccuracy in position and the inaccuracy in momentum, that will be always greater than or equal to h upon mv, this one. Okay, so delta x into m delta v, that will be greater than or equal to h upon mv. So this one here. So inaccuracy in momentum will be how much? About that we can find out. So that is given here. So delta v h upon 4 pi delta x m, delta x, as you know, delta x into delta p, that will greater h upon 4 pi. So delta x into m delta v, that will be greater than or equal to, that will be greater than or equal to h upon 4 pi. So inaccuracy in momentum, so delta v, that will be greater than or equal to, so delta v will be, that means inaccuracy in velocity, that will be greater than or equal to h upon 4 pi into delta x this side and m, that is here h upon 4 pi delta x into m, greater than, at most what can be happen, at most that can be equal to. So that's what delta v, that has been calculated by putting the value of h as 6.6 into 10 power minus 34, 4, and pi is 22 pi 7. Delta x is given here already 0.1 angstrom and m is here. So 4 into this one 3.14 or 22.7, 22 by 7, 0.1 into 10 minus 10 meter, this one 9. It is of the electron. Here, so mass of electron is here 9.1 into 10 power minus 34 joule into 9.1 into 10 raised power minus 31 kg. That has been calculated because mass of electron is that much. So this is the value. Okay, next question, watch out. Golf ball has the mass 40 gram and speed has been given. Speed is calculated by accuracy of 2%. So uncertainty in the position will be how much? So already here uncertainty the position is through 2%. So how much inaccuracy there is uncertainty? So that means inaccuracy is there 2%. So velocity is given here 45. So inaccuracy will be 2% of 45. 2% of 45. The answer in the speed is 2%, that is this much. Here is something you write, that is 45 into 2, because 2% of 45. Why this one is? Because that is 2% of 45. That means 2 into 1 by 100 into 45. That is. Okay, same. So 0.9 meter per second. So you know already delta x delta v equal to will be greater than or equal to h upon 4 pi. So by that value delta x can be calculated. That is inaccuracy in the position. Inaccuracy in the momentum was 2%. So that was the inaccuracy in the velocity, and inaccuracy in the position will be that much. That's why. Okay. Now, what's the significance of Heisenberg's uncertainty principle? The Heisenberg's uncertainty principle have explained here due to the Heisenberg's uncertainty principle, the Bohr's atomic model was discarded here, because what here Bohr's atomic theory stated that the electron revolves around the nucleus in a definite circular path, which is called orbit. But that can be stated only when both position and momentum of electron could be calculated accurately. But according to Heisenberg's uncertainty principle, both position and momentum of electron could not be calculated accurately. That's why we cannot say that the electron will revolve around the nucleus in a definite circular path. But guys, it not means that there is no relevancy of the Niels Bohr's atomic theory of wide phenomena explained by the Niels Bohr's atomic theory. Okay, so we cannot ignore the significance of the Niels Bohr's atomic theory. So then after, the quantum mechanical model of atom was proposed. After this one, the quantum mechanical model of atom was proposed. So about that, there will be what the orbit, what is orbital, and what is here there will be Schrödinger's wave equation. Schrödinger's wave equation you will not have to study in detail, but in the IIT main and in case of IIT advanced, question asked from there about the nodal surface, questions asked from there. That's why we will also discuss about the Schrödinger's wave equation, something more provided in the NCERT book. Okay, so it's all for this class. In the next class, we will discuss from here the quantum mechanical model of atom. Okay, so it's all for this class. Thank you, Team Educate.